This is a focused discussion of the kinematics, kinetics, and EMG at the ankle during walking. So let's start with the ankle angles. We can see here is data from a study of people walking at different speeds, and we can see the hip, knee, and ankle angles. We're going to focus on the ankle angles here in the bottom right. We can see the normal curve first. At initial contact, here is 0, and the 100 represents the subsequent toe off of the same limb. At approximately 60%, here would be toe off, would represent the stance phase. From 0 to 60 is stance, and from 60 to 100% is swing. So we can look here and see that the dorsiflexion angles, which are positive, and then plantar flexion angles, which are negative, what the pattern of range of motion is throughout a gait cycle. The first part of stance, which 0, initial contact to weight acceptance, 0 to about 10%, we can see that the ankle goes through, starts in slight amount of dorsiflexion, plantar flexions somewhat, and then returns to a stable 0 position, and then progresses into dorsiflexion during this single cingulum support phase from about 10% to 50% of stance right here. And throughout that entire period of mid-stance here to 30% and then terminal stance, the ankle's gradually dorsiflexing. It reaches its peak dorsiflexion right around the point of transitioning from terminal stance to pre-swing, or just after that. We can see here's, for example, peak dorsiflexion at the slowest speed. So this would be the slowest speed, and the ankle angle is just above 15 degrees. After it reaches its peak in a very short period of time, so just at the transition to terminal stance, it rapidly plantar flexes, reaching its peak plantar flexion, really coincidence with toe off on that same side. After the limb is free from the ground and the swing has begun, we can see that the limb goes from that peak plantar flexion position, and by mid-swing is into its dorsiflex position, and then is returning back to an initial contact point angle about around a slight dorsiflexion for a subsequent initial contact. So what we'll explore in the kinetics is what's important about this first weight acceptance phase of going from a relatively minor base of support with the heel contact to foot flat to give us good support, tibial progression that occurs across this terminal stance and mid-stance and terminal stance phases, the rapid plantar flexion that's associated with pre-swing, and then the importance of dorsiflexing the foot for limb advancement and prevention of tripping during the swing phase. So now we're going to look at a typical ankle moment graph. Again, the 0 point on this graph is initial contact. The 100% point here to the right is the subsequent initial contact, and 60% is marks the toe off point during that one cycle. So from 0 to 60% is the stance phase, and from 60 to 100% is the swing phase. And we can note here that the internal plantar flexion moment is plotted as positive on the y-axis, and the internal dorsiflexion moment is plotted as negative. So we can see at initial, and then here's a picture of the ground reaction force relative to the limb in several different points along the cycle, and we'll kind of match these up as we go along. So let's start here at initial contact, and we can see that the graph's telling us that the minimal agonist activity, because that's after all what the moment data tells us, is a dorsiflexor moment. So internally we're generating a dorsiflexor moment, or the anterior tibialis muscle is anticipated to be active. So let's look at how that appears on the drawing. So the person's landing on their heel, so the ground reaction start point is at the heel, and it projects up toward the center of mass of the body, which goes slightly behind the ankle joint center. Because it's behind the ankle joint center, there's an external plantar flexion moment, so the ground reaction force is tending to plantar flex the ankle. So internally, we have an equal and opposite moment that is in dorsiflexion. And that's the weight acceptance phase moment data for the ankle that occurs here from 0 to approximately 10%. After 10% of stance, mid-stance is seen. We see this kind of gradual increasing plantar flexion moment internally that continues to progress into terminal stance all the way to the transition from terminal stance to pre-swing. And so what this picture here is showing us is that this is the transition from initial contact to the end of loading response. And the end of loading response, the tibia is vertical. And as the tibia switches from an anterior tib kind of control mechanism to the plantar flexors, and in particular the soleus. And why would the soleus be active here? Because the knee is also bent at this point. And we'll see that in another graph where we look at the knee angles. But essentially, so the soleus now is in a position to control the advancement of the tibia over the fixed foot, which is firmly planted on the ground. And we can see how it rocks forward here. So we get this tibial advancement or dorsiflexion from the ankle. Okay. Then at approximately, so that explains this kind of gradually increasing moment data. Okay, as the person's opposite limb is swinging forward, the tibia is advancing, and that's being controlled by the soleus muscle. Remember, this is this period of single limb support. Okay, so what happens then as we transition from this single limb control and this tibial advancement, controlled tibial advancement, the opposite limb makes heel contact, which is around 50% of the gait cycle, and that triggers this transition from one foot to the other. Part of that transition from one foot to the other is shifting weight onto that opposite limb, and as part of that process, we have a rapid plantar flexion activity of the ankle, and with that, when that occurs, the knee is also straight. And so because of that rapid plantar flexion, that's both the gastroc and soleus muscles are involved in that, we can see that the effort from the ankle will push the center of mass upward and forward, assisting the transition to the opposite limb. And so that's why it's not just called terminal stance, but may also be called push-off, because this rapid plantar flexion is also associated with an upward and forward projection of the center of mass of the body and assists with this shifting from one leg to the next. And then finally, after we have that successful transition to the opposite limb and that toe comes off, we see this slight dorsiflexion moment. And there's no ground reaction force at this point, but we can see here that the tibialis anterior muscle is shown being active, because essentially we need that muscle to take the foot out of that plantar flexion position and return it to a dorsiflex position to clear the foot as we're moving the swinging limb to put the tibia vertical as we transition to terminal swing. Now, how is this reflected in the EMG and power data? And just recall that the power data is a combination of angular velocity from the angle data and the moment data. And so essentially what the power data helps us with is understanding when eccentric and concentric contractions are occurring, and to what degree the angles and the moments are kind of working together to tell us how much energy the muscles are generating, and therefore helping us move. So there's essentially two key bursts associated with the ankle power graph, and we can see here this vertical axis is power, and this is a positive power, indicates a concentric energy generation from the ankle, and a negative power indicates an eccentric contraction. And so we can see the first burst, which is really not a burst, but a period of eccentric contraction over much of the stance phase of gait until approximately 30 to 40%. And so here again we have initial contact and then 100%, and that'll be pretty consistent with the other graphs coming up. And so we can see essentially as the foot lowers to the ground, there's a small eccentric contraction associated with the tibialis anterior, but then much of the plantar flexion contraction that we notice in the agonist activity identified by the moment data is that's from the soleus is an eccentric contraction where it's allowing that tibial progression to occur. And then what we see is this rapid switch from eccentric to concentric that's occurring somewhere around 40% of the gait cycle. And that gets underway and then peaks at several times body weight. So this is the power data normalized to body weight. And this is speed dependent, and that's what we see in this graph. So the slower speed is the dotted line, a moderate speed is this dark line, and the lighter line is a fast walking speed. So we can see that basically the eccentric contractions are affected less by speed, but as we speed up, we have this large concentric burst from our ankle plantar flexors as we transition from terminal stance to pre-swing. We can see that this is a really important modulator of how fast we walk and our ability to walk at faster speeds. And so the push-off that's identified by this power data is really important clinically and helps us walk with greater effectiveness. And now we're going to combine the data from the kinematic power data with EMG. And so basically the issue for us is that we don't really, the agonist muscle contributions or the kinetics that are essentially captured in the power data here with eccentric concentric contractions don't help us understand the potential for co-contractions to occur. And so we have to look at the EMG data to verify which muscles underlie these kinetic patterns. And so we can see we have plotted three key agonists at the ankle, the tibialis anterior, gastrocnemius, and soleus muscles. And we can see that at initial contact here with this same kind of moment data, which is indicating that there's an external plantar flexion moment, so we need the anterior tibialis muscle to control that. We can see that it's there for us in terms of the EMG data. So the motor control pattern from the central nervous system is tapping into this, the anterior tib agonist activation. And really the gastrocnemius activation is fairly minor, and so it's not considered a significant co-contraction, and the same with the soleus. So fairly uniform agonist activation with little co-activation at initial contact, at least with respect to the sagittal plane. And so this angle that we see, this descent of the foot, is primarily the responsibility of the tibialis anterior and likely the other dorsiflexors like the extensor digitorum and the extensor hallucis muscles. And so then what we can also see is that as we go into late stance and as we transition to swing, there's another burst, although relatively small, of the tibialis anterior muscle, and that's illustrated here, kind of matching up with this idea of clearing the foot for limb advancement and preventing tripping. So we have a slight activation of tibialis anterior muscle during swing to help clear the foot. Okay, so that's really the dorsiflexor's role. So now we want to look at the gastroc-soleus role. And we can see here is really what we're talking about is this control of dorsiflexion that's occurring after weight acceptance throughout stance, really. And then this rapid plantar flexion that's occurring as we go through the pre-swing phase of the gait cycle. And so if we look here, we can see that really the gastroc has its big burst toward, just as the 60% gait cycle point here, toward the end of terminal stance and pre-swing. We can see that there's a gradual increase in activation in the soleus muscle throughout the stance phase up to when the toe comes off. And so essentially the mechanics and the EMG both support the idea that this tibial advancement that's reflected here in the gradual increase in dorsiflexion that occurs across the stance phase is, and identified by the power graph as an eccentric contraction, is primarily the role of the soleus muscle. And then as we transition to pre-swing and we see this rapid plantar flexion, that corresponds to this large power generation from the ankle that's so important for modulating speed. Primarily comes from the combination of the soleus and the gastroc muscle, but the gastroc muscle at this point is much more important. So this comes up at least a couple times during gait in terms of helping us control proximal movement. And so there's two key points that we're going to make with this graph. And the first key point is that after foot flat, the tibia must be stable for the femur to rotate forward, or else first to get knee extension. So this first area, so soleus assist, extend the knee. So how does the ankle actually influence proximal muscles? And so that's kind of what this slide is about. So key one is that once the foot's flat, the tibia has to remain stable, because what we're essentially going to have is we're going to have a very rapid movement of the femur forward. We can see it's angled back here, and then now it's even with the tibia, or we could say it's the knees flexed here at the 15% point, and then as we move to the 30% of the cycle, the knee is going to be relatively extended. Okay, so the first and critical point for the interaction of the proximal muscles is that the tibia has to be stable and vertical, and has to progress slower than the femur for the femur to effectively advance the hip or the trunk forward. And so this is the first key, and we see this failure in this will affect several types of neuromuscular problems during walking. The second key is at push-off. So here we see this 45% cycle position, is that the knee must be straight for the ankle plantar flexion to push the pelvis up and forward. So essentially, if the knee's straight here, we can see that if we plantar flex the ankle rapidly and hard, what will happen is all that energy will be immediately transferred to the knee, through the knee, and to the trunk. And that the effect of that contraction, we can see here in an arrow, the gastroc will push the trunk upward, which gives us better support. And the soleus muscle is effective at pushing the trunk forward, which is the goal of gait in terms of forward progression, which assists with the transitioning of the heel strike and weight acceptance onto the opposite limb. So there's two key things that affect the transfer of the ankle energy up to the trunk and makes walking effective. One is during the weight acceptance phase, and throughout mid-stance, is that the tibia advancement is controlled sufficiently to allow for the proximal muscles to modulate the femur movement and move it more rapidly than the tibia, placing the knee in extension. And the second key is that the knee is straight when during terminal swing, or pre-swing, terminal stance and pre-swing, so that the ankle plantar flexion that does occur effectively lifts the trunk up and forward. So based on the three ankle angles, so we can see that during weight acceptance, the foot goes from a dorsiflex to a plantar flex position. That's called the heel rocker. And the progression of the foot from throughout dorsiflexion, from weight extend throughout the single limb support phase, so from about 10% to 50% of the gait cycle. That's called the ankle rocker. And then the final part of the ankle movement, when it rapidly plantar flexes through pre-swing, that's called the forefoot rocker. So know the three rockers and their definition. That's commonly used terminology clinically. So how can we use this to cue us in of what to look for clinically? Well, at the initial contact point, it's important that the people are dorsiflexed so they can have a smooth transition to weight acceptance. So if they're plantar flexed, that's going to stop forward progression and immediately affect the gait cycle. We know that after weight acceptance, they have to have this kind of gradual tibial advancement, but it can't be too fast or it'll mess with the ability of the femur to progress the trunk. And so essentially, if we have excessive tibial advancement at foot flat or thereafter, that can also be a problem clinically. We also saw this rapid plantar flexion that's important for push-off. And so if there's decreased plantar flexion at push-off and instead a pull-off, that also can indicate a problem with the plantar flexors. And then finally, what might contribute to tripping and different problems like this is we can see there's this necessity for us to go from plantar flexion to dorsiflexion. If there's insufficient dorsiflexion during swing, that could contribute to tripping. Okay, so that summarizes some of the key issues during gait that have to do with the ankle.